Next, we will talk about the graph coloring problem. And this is the problem of the assignment of labels, which we call the colors usually, to the elements of a graph under certain constraints. Okay, so graph coloring problems can be associated with edge coloring or face coloring, or rather vertex coloring. And the other ones, can be transformed into vertex coloring. Therefore, we usually mean vertex coloring when we say graph coloring. So you have a graph, something like this, and a graph coloring problem is usually means assignment of colors to each of the vertices so that this and this is satisfied. For instance, so that one of the classical ones is so that no two vertices that have an edge between them have the same color, for instance, or assign colors of one of the two colors to each vertex so that a special property is satisfied, etc. Now, the least number of colors required to color a simple graph so that no two adjacent vertices are assigned the same color is called the chromatic number. So this is the problem I have just mentioned. You have a graph, a simple graph, and you want to color each vertex so that when two vertices have an edge between them, meaning that they are adjacent, they do not have the same color. So this is similar to coloring a map. Let's say you have the cities mapped out, and let's say you have the map of Turkey in front of you. The city boundaries are drawn. Assume that each city corresponds to a vertex, and neighboring cities, they have an edge between them. So this problem corresponds to coloring this map in such a way that no neighboring cities have the same color. Okay, so this problem is quite a significant problem because it has applications in a wide variety of algorithms, such as scheduling and constraint satisfaction. For instance, sports scheduling, like maintaining a schedule of matches so that there are no conflicts of teams or sports people, or seating plans in an area, and exam or course timetabling in a school like a university, or airline flight scheduling so that no two planes overlap, etc. And bandwidth allocation in communications, or in computation theory, you have compiler optimization also, and an application of graph coloring problem. So you see, it looks like a very simple problem, but it has many practical applications. So this is a significant problem. And also attached with this problem, we have a very significant theorem called the four-color theorem. And it states that every planar graph is four-colorable. This means, in a sense, when you have a planar simple graph, the number of colors required at most to color the vertices so that no neighbors have the same color is equal to 4, or the chromatic number is equal to 4 for planar graphs. Now, this problem or this theorem is important because of the way it was proven. It was proven by these people, Apple and Haken, in 1976, using a computer-assisted proof. So what they did was they specified certain properties that a solution has to satisfy for graph coloring, and then they also classified all possible graphs in a number of, in fact, a large number of classes according to certain properties. And then one by one, they had the computer check whether 4 is the maximum for each of those categories. So at the end of the day, it was a brute force method. The list was quite large. It was so large that a person wouldn't be able to do it on paper, but a computer completed it. And when they published their results, some people did not accept it at first because, well, it didn't look like we have a way to actually check whether this is correct or not. But eventually, some people also worked on the correctness of this proof, and some other people also formalized the proof so that a computer program also verifies this computer proof. So now it is established that this proof is true, and it's one of the first examples where computers were used as a proof assistant. So it has a historical significance in theorem proving and computation theory. Okay, so a graph coloring problem is also related to bipartite graphs, and let's define what a bipartite graph is. A simple graph is called bipartite if the set of vertices V can be partitioned into disjoint V1 and V2 subsets such that each edge in E connects a vertex from V1 to another in V2. So simply put, you have these vertices in your graph, but you want to partition them into two so that all the edges connect one vertex from one of the sets to another vertex in the other one. So you see A, B, C, D form V1 in this example, and E, F, G form V2, and A, B, C, D do not have any edges among them. And similarly, E, F, and G do not have any vertices among them. So when you set up the adjacency matrix of such a graph, you see that that matrix turns out to be a block diagonal matrix where you can make an upper left block as all zeros and a lower right block all zeros, and all the connections are from one block to the other. Okay, and bipartite graphs has a lot of applications again, and here we have a theorem regarding them. Simple graph is bipartite if and only if it is possible to assign one of two different colors to each vertex of the graph so that no two adjacent vertices have the same color. I mean, this is long to pronounce, but its meaning is simple. It just says that for a bipartite graph, the chromatic number is simply 2. And that is obviously true because you just assign one of the colors to V1 and the other color to V2, right? So this will have one color because none of them are neighbors. And this will have the other color so that all neighboring pairs will have different colors. Simple as that. So checking for bipartiteness is not that difficult.